We've chosen a periodic basis, we even called it a Fourier basis, and we want to express the data as a sum of constants times our basis functions, which is the sum for frequencies for index 0 to 1/2 of n of cosine coefficients times cosine functions plus sine coefficients times sine functions. This will be a Fourier series expansion. But how do we transform the data values into the expansion coefficients? Well, it depends on the fact that for the frequency being one of the Fourier frequencies, we have the following property. The sum over all possible times of the cosine of 2 times pi times frequency times time is equal to 0. That's because every set of observation times completes a full number of cycles. The same is true for the sine function. Unless, of course, the frequency is 0, in which case the sum of the cosine is the sum of 1, which is just however many data points we've got. Now we can use the angle sum and angle difference formulae to notice that if we take cosine at one frequency times cosine at a different frequency, we can express it as a sum of single cosine functions. We can do the same for sine at one frequency times sine at another frequency. And we can even do so for sine of one frequency times cosine of another frequency. What we've done is, instead of having a product of trig functions, we've just got a sum of trig functions at frequencies which are sums and differences of our original beginning frequencies. Now, this enables us to compute the sum over all observed times of the products of basis functions. The sum over all observed times of the cosine of a frequency times time times the cosine of a different frequency, or maybe the same one, but another one times time, is going to be equal to n, the number of data points, if both these frequencies are the 0 frequency. It's going to be equal to 1/2 of n if both these frequencies are the same but not the 0 frequency, and it's going to be 0 if they're not the same frequency. Likewise, the sum of the product of sine functions is going to be 1/2 of the number of data points if they're the same frequency but not 0, and it's going to be 0 if they're different frequencies. And finally, the sum over all times of the sine at one frequency times the cosine at any other frequency, even if they're the same frequency, is going to be 0. Well, this tells us that our Fourier basis is an orthogonal basis, meaning that any two basis functions that are different are orthogonal to each other. They have an inner product of 0. But to make that happen, we have to define the inner product as proportional to the sum over all observed times of products of basis functions. That's why we chose the frequencies we did, so the basis functions would be orthogonal. We'll choose the constant of proportionality as 1 divided by the number of data points, so the inner product of two functions is 1 divided by n times the sum over all times of one function of time times the other function of time. When we do that, we have the following set of inner products of basis functions. The inner product of two basis functions is equal to 1 if they're both the unit function. It's equal to 1/2 if they're the same function but not the unit function, and it's equal to 0 if they are different basis functions. That's what makes them orthogonal. If we start with the Fourier series expansion, we say that our data is some sum of coefficients times basis functions. Let's take its inner product with a cosine basis function at a non-zero frequency. That's the sum, 1 divided by n of the sum, times data values times our basis function, the cosine function. Well, then, all the terms are going to drop out, except that for which the frequency in our Fourier series expansion is equal to the frequency that we're taking the inner product with. And that's going to leave us with 1/2 of the cosine coefficient. So the cosine coefficient turns out to be 2 divided by n times the sum over all times of data values times cosine at that frequency. An exactly similar argument shows us that the sine coefficient is 2 divided by n of the sum of data values times the sine function at that frequency. And finally, we have the single exception, the zero frequency term, for which the cosine coefficient, which is just the zero frequency coefficient, is the average data value. Now, the key to being able to compute the coefficients in this manner is that when our basis functions form an orthogonal set, not necessarily orthonormal, but at least orthogonal, the expansion coefficients are given by this expression. Expansion coefficient is the inner product of basis function with data divided by the inner product of basis function with itself. By the way, note that there's no sum over index k. We're not using any Einstein summation convention here. This particular simple formula is possible because of an orthogonal basis, which means that an orthogonal basis is actually a very friendly basis. An orthonormal basis would be ideal, but we'll get to that in a couple of minutes.